A molecular formula provides an inventory of atoms, carbon, hydrogen, and oxygen. The resulting molecule's physical behavior depends on how those atoms link together. Take the formula C3H6O. This inventory of 10 atoms constructs distinct chemical universes. Connect them linearly, placing the carbon-oxygen double bond at the end to build propanol, a highly reactive aldehyde. Shift that exact oxygen inward, bonding it to the central carbon, and the structure becomes propanone. Break the carbon-oxygen double bond, form a carbon-carbon double bond, and attach a hydroxyl group. The inventory produces allyl alcohol. Or loop the chain back on itself, trapping the oxygen in a four-membered ring to form oxetane. Looking at a bar chart, the boiling point plummets steeply as we move from the hydrogen-bonding alcohol down to the strained cyclic ether. This is structural isomerism, often called constitutional isomerism. It is the rule that identical atomic inventories can possess radically different connectivities. The true identity of a molecule relies strictly on topological reallocation. To predict a chemical's behavior, you must map its structural boundaries. Functional isomerism is a rearrangement of atoms that forces a molecule into an entirely different homologous series. Changing the functional group rewrites the molecule's reactive capabilities. We map these structural shifts using fixed rules called homologous dyads. Take the general formula CnH2n plus 2O. This mathematical ratio dictates that the molecule must take one of two paths, an alcohol or an ether. Contrast ethanol with dimethyl ether. The alcohol path creates a polarized oxygen-hydrogen bond, allowing for strong hydrogen bonding. The ether structure traps the oxygen between carbons, preventing those interactions entirely. The second dyad rule applies to the formula CnH2nO. This specific ratio guarantees the presence of a carbonyl group, mapping exclusively to aldehydes and ketones. Adding a second oxygen gives us the formula CnH2nO2, which forms the third dyad. This locks the molecular possibilities into carboxylic acids and esters. We see the same behavior in the nitrogen dyad, where the attachment shifts from a carbon atom in cyanides directly to a nitrogen atom in isocyanides. Recognizing these fixed formula dyads allows chemists to narrow down the universe of possible structures before drawing a single bond. Within these general formulas exists a polyvalent constraint. Certain functional groups act as fixed bridges, locked permanently within a carbon skeleton. Metamerism is a specific isomerism that occurs only when the distribution of alkyl groups on either side of one of these polyvalent bridges is altered. There are four primary polyvalent bridges that permit metamerism: the oxygen of ethers, the sulfur of thioethers, the nitrogen of secondary amines, and the carbonyl group of ketones. Look at the structure for diethyl ether. The oxygen bridge is flanked by 2 carbons on the left and 2 on the right. A metameric shift occurs when we alter that partition. By moving 1 carbon from the left over to the right side of the bridge, we create methyl-propyl ether, resulting in a 1:3 distribution. This definition separates metamerism from standard chain isomerism. If the overall distribution size across the bridge does not change, it is not a new metamer. For example, branching the 3-carbon chain of methyl-propyl ether into an isopropyl group creates a chain isomer. Because the partition remains locked at 1 and 3, the metameric distribution is unchanged. Metamerism is solely a function of carbon partitioning across a rigid functional boundary, distinct from the internal branching of the chains themselves. The hydrogen count dictates a molecule's geometry. Bending an open carbon chain into a closed ring extracts a strict mechanical toll. To make the connection, 2 terminal hydrogen atoms must be removed. Forming a carbon-carbon double bond, a pi bond, extracts the exact same stoichiometric toll. 2 hydrogen atoms are lost. This balancing scale illustrates ring chain isomerism. It demonstrates that open chains with pi bonds share identical molecular formulas with saturated cyclic structures. The general formula CnH2n dictates this trade-off. Hex 1-ene is an open chain containing exactly one pi bond. That exact same C6H12 formula maps perfectly to cyclohexane, a structure with 0 pi bonds but 1 ring. The rule compounds. The formula CnH2n-2 removes 4 hydrogens. This means the molecule must contain either 2 pi bonds, like a diene, or a combination of 1 ring and 1 pi bond, creating a cycloalkene. Rings and pi bonds are stoichiometrically equivalent topological choices. Chemists can mathematically predict cyclic potential from the molecular formula alone. To dismantle complex molecular formulas without memorization, we run the data through an analytical sorting matrix. Step 1. We input our target test formula, C4H10O. By determining the general formula, the matrix highlights the CnH2n plus 2O pathway, isolating our functional groups to alcohols and ethers. Step 2. We isolate the alcohols to map position isomerism. We start with butan 1-ol, then move the hydroxyl group 1 position down the primary carbon chain, generating butan 2-ol. Still on step 2, we map chain isomerism. We branch the main 4-carbon skeleton into a 3-carbon isobutane base to form 2-methyl-propan 1-ol. Step 3, we isolate the ethers to map metamerism. We plot the carbon distributions across the oxygen bridge, shifting from the symmetrical diethyl ether to methyl-propyl ether. Finally, we map the overarching functional relationships. The alcohol pathway and the ether pathway share the exact same formula, making every structure in the left cluster a functional isomer.